Hello everyone, welcome to today's ASP seminar. Today we are very happy to invite Ming Yuxu, a recent scientist at the Baidang team, who is working on the multimodal interaction and word model team. He will talk about DeltaFormer, breaking the expressiveness of transformer with delta rule. In this paper, which is called Understanding Transformer from the Perspective of Associative Memory.
Thank you. Let's begin. Good afternoon, everyone. I'm Ming Xu from Better Dance. I'm very honored to have this opportunity to share our work at the ASAP seminar. Today, I will share our research understanding transformer from the perspective of associative memory, which I work on with my partner Shuzhong, Tenlong and Guangshi. Thank you for your attention and support. Let me introduce our work in detail. Thank you. This presentation is divided into three main parts. Firstly, we will explore the associated memory and its capacity. Specifically, we would like to answer such a question: why is transformer so useful? We will explore the concept of associated memory and analyze its role in transformers. By understanding the associative memory, we can better explain the powerful capabilities of transformers. In addition, how do existing methods for updating memory work? We will review and analyze the current methods to update memory, including the role of attention machine and other related works. Finally, we will look into the exploration of next generation models. Specifically, we would like to answer such a question: how to enhance transformers with powerful updating rulers. Based on the analysis of transformer with powerful updating rulers, we will propose some ideas to improve the memory updating machine of transformers, thereby enhancing their expressiveness. Before we dive into the main content, I would like to discuss an interesting topic: the contradiction between expressiveness and parallelism. Question 1. If you can add any two numbers in parallel each time, how much time do we need to calculate the sum of n elements? The answer is O log n. Similarity: if you can add any two numbers in parallel each time, how much time do we need to calculate the sum of two metric with size n times n? The answer is O1. We can find that the time complexity for question 1 is greater than that of question 2, but the total number of operations of question 1 is small. In fact, theoretical computer scientists of the last century conducted in-depth research on this, mainly based on three questions. The category of parallel complexity has been divided. The first question is, what are the operations allowed for a single node? There are generally two types. The first type allows only two Boolean operations of AND, OR, and NOT. The second type adds a threshold gate to the first type, which activates when the input result exists a certain threshold. The second question is, what is the allowed number of input for each node? The first type is 2, and the second type has no limit. The third question is, how long is the longest path, which can also be considered as the depth of the model. Based on these questions, we can obtain a rough classification of NCI, ACI, and TCI. Here, I have listed some common parallel complexity classes and the problem within them. As we can see that a model with high parallelism will solve little problems. Then a natural question is, what complexity class are the current large language models in? The answer is AC0 or TC0, depending on the precision of the model. But regardless, its complexity does not exist TC0. This also means that for transformer-based models to perform tasks out of TC0, it is difficult to provide an answer in one step. They must rely on the chain of thought to generate tokens step by step and finally obtain the correct answer. To some extent, it also reflects the limitation of transformer architecture. On the other hand, if we look back at the history, how did transformer defeat LSTM in recent years? One of the very important reasons is the widespread application of GPUs and the high parallelism of transformers, which can fully utilize the computing power of GPUs. However, we know that there is a fundamental contradiction between parallelism and expressiveness. However, models with high computation depth like LSTM are difficult to parallel on GPUs. The next question is, can we find a model that can perform efficient parallel computing on GPUs and has higher performance than transformers? The answer is yes. In fact, DeltaNet can achieve it. Firstly, what is the DeltaNet? In fact, relevant research has already been conducted in the 1990s and 1980s. For example, the one on the left is a formula from Sutton's paper published in 1980. On the right is a formula with DeltaNet, which has been more widely used recently. The core of DeltaNet lies in what we expect the internal output to be consistent with the feedback, and we adjust the internal state based on the inconsistency with the learning rate. And regarding this updated ruler, it can have expressive power beyond TC0. Readers can refer to the following work. But how can such a method be efficiently parallelized on GPUs? It seems like we need T loops if the sequence length is T. Fortunately, Song Yang discovered last year that there is an efficient parallel solution for this type of network on GPUs. If you are interested at this point, I highly recommend that you read her paper. But the story hasn't yet stopped. Methods with limited state space like DeltaNet also have some other essential problems, such as weak memory abilities. However, the transformer is different. This is also an important reason why transformer become popular. Therefore, a natural idea is to combine transformer and data rule to enhance the expressiveness of transformer. Okay, the first part is about associated memory and its capacity. I think it's a very important aspect of understanding transformer and know transformer architecture. Associative memory is defined as ability to learn and remember the relationship. Yes, feel free to leave any question in this chat. For example, we associate Paris with Eiffel Tower. To some extent, it is also a learning of occurrence. We will connect things that frequently appear together. Like a dictionary, we have keys and values. Learning is the process of acquiring the fuzzy mapping. After we learn something, the process of using it is to use a query to retrieve the corresponding value from memory. As early as 1972, Her proposed it. We can find that when the keys are orthogonal, we can use the sum of the outer product of the key and value to store memory. This kind of outer product memory is also known as linear attention. Unfortunately, keys are not always orthogonal. If the keys are not orthogonal, it is not easy to obtain the information perfectly. We can observe that the noise turn outside of the signal turn is not always zero. Therefore, we define a metric inverse retrieval SNR. Its numerator is a noise turn, and its denominator is a signal turn. A larger value indicates a higher noise component, resulting in lower retrieval accuracy. Considering keys and values are IID standard Gaussian vectors, we can calculate the inverse SNR as follows. And then we can find that the linear model with vast dimension d must grow linearly with a sequence length n. This may explain why linear attention usually has poor retrieval performance. So, what are the ways can we increase our memory capacity? In fact, using an ancient method named kernel trick can increase memory capacities. Kernel trick introducing a kernel function kappa xy equals phi x phi y. Phi maps keys into higher dimension space. Then we can calculate the metric, the inverse of SNR that we previously defined. The current expression is as follows. The numerator is the noise turn, which means how much the kernel suppress irrelevant features. And its denominator is the signal turn, which means how much the kernel amplifies the matched features. Taking the common softmax attention as an example, we can observe that as long as d equals O log squared n, the model can efficiently complete the memory. This can also explain why softmax attention has good retrieval abilities. On the other hand, I strongly recommend readers to read Understanding Transformer Reasoning Capability with a graph algorithm about the ability of transformer to perform some other operations. Then we have discovered some interesting phenomena in language modeling. Firstly, increasing the head dimension is beneficial for the performance of the model. This is not only in the linear model, but also for transformer. However, the improvement in linear attention is even more significant. Secondly, slightly reducing the temperature of softmax is also beneficial for improve the model's retrieval abilities. Finally, the reduction of head dimension has a smaller negative impact on softmax tension than the increase in diversity. So softmax attention can benefit from multi-head attention. However, the linear attention model is different. We can also understand FFN as associative memory, just different from attention. FFN's memory is more long-term memory, while the key value pair in attention is a more short-term contextual memory. And the kernel function in FFN has become a ReLU function. Then we have discovered some cross-design between attention and FFN. Actually, we have reviewed early papers on attention is all you need. They have discovered similarities between FFN and attention and conducted experiments. But in the end, for efficiency reasons, they choose the form we are currently familiar with. They also try to use multi-head attention in FFN. Another thing is the sparse attention machine, which can also be considered as an application of MOE in attention layer. In addition, use some gate into attention is also an option. Uh, okay, let's move on to the second part. In
I
the
have,
previous section,
I have a question. The
okay,
Do you have analysis for like FFN with ReLU activation or a switch glue, no, a switch activation function? Do they have any memory capacity difference using this sort of different kernels?
Uh, according according Anthropic's blog, the ReLU's function has more powerful regarding the superposition. Maybe ReLU's function has more memory, but considering attention, the attention mapping is always sparse, so the softmax tension may have some advantages. Uh,
Can
yeah,
I also
that.
ask you to go back one more slide just to that last one we didn't, and maybe cover that a little more in depth about the
Uh,
gating?
the gating.
Yeah, thank you.
Oh yeah, conduct in the about this. We can find that gating like switch glue is underexplored. And Fox we know is a work in Eclair 2025. I think they Fox is also use some gate, and we can rewrite them as a unified form like this. Uh, uh, which is a good question. Uh,
Yeah, I guess
maybe
one
we
question
talk
I
about
had was, do you see some interaction with that and memory capacity?
that we think. Uh, okay. Uh, personally speaking, the gate machine doesn't increase the memory capacities. Uh, yes, it's only increase the approximate power of neural network, I think.
Yeah, do you have any proof in the paper so we can better check it afterwards?
You got any preference? Uh, uh, I think uh, maybe we can talk it later. I
Yeah, sure,
currently
sure.
have no idea.
Yeah, sure, sure, sure. Please go ahead. Thank you for your
Uh,
answer.
okay, let's move on to the second part. In the previous segment, we mainly reviewed the memory capacity of different methods. This part is about studying the ways in which different memories are updated. Because learning is a dynamic process, as the information increases, the memory will also update. Taking the linear model as an example, we write the memory of linear tension in recurrent form. We can get St is equals to St sub 1 plus the outer product of Vt and Kt. Then we can consider the second term as a gradient of a loss function with respect to t. In this way, we can understand this equation from the perspective of one-step gradient descent. So what is the loss function? The loss function is LT of st sub 1 equals negative st sub 1 kt inner product with Vt. However, the loss is abounded and there may be optimization issues. So what should we do? The first solution is to regularize S. Then we can find the updated ruler of gated linear tension. Gated implying a bias that older information is less important. Then the second solution is to regularize SK. Then we can find is the delta net. So how to understanding the magic gate? We can see that delta rule is a smarter gate for erasing overlapping historic informations. And the third way is to reduce the learning rate as the sequence length increases. This is the normalization of synaptic tension doing. This part is very quick. Then after introducing the memory capacity and memory updating rulers, we now move on the part 3, which will explore the model architectures. Firstly, there are two different ways to avoid optimizing S into unbounded. What is the fundamental difference? One is to use decay. The other is using delete. For the former representative architecture, including RedNet, RWK4, and for the latter, include RWK7, DeltaNet. After some deduction, we can introduce immediate variables to better express these two expressions. For decay, we introduce an immediate variable beta. So the S can be written as an equation related to beta as well as all the keys and values in history. For decay, we introduce an immediate variable ut, so that S can be written as an equation related to U as well as all the keys and value in history. So the key to the problem become how to efficiently calculate beta and U. Intuitively speaking, the computation of beta can be treated as a prefix sum, which allows for an efficient implementation. However, the computation of U seems to be sequential, requires OT loop. This actually reflects that the parallel complexity behind these two things is different. The parallel of beta calculation is high, while the parallelism of U's calculation is lower. Therefore, models based on DeltaNet can have more depth and solve a wide range problem with the same number of layers. The following are the complexity range of some common models that we have summarized. The higher the parallelism, the lower the expressiveness, and we list the representative tasks of common complexity next to them. And we can see that there is many important tasks is beyond TC0 which transformer lies, such as Python code evaluating and chess. So when transformer learn tasks beyond TC0, such as track the swap of 5 elements, what will happen? Firstly, we can observe that the model is very difficult to learn from data. It takes almost 16 layers to learn an exchange with a length of 32, even if there are only 5 elements. Secondly, it is difficult for the model to generalize its length after training. After existing the training length, it fails. One of the main goals of our work is to make the transformer more powerful than TC0. A natural idea is to combine the contents of the previous two chapters. On the one hand, using kernel function to enhance model capacities, and on the other hand, using data rule to improve model performance. So we rethink data rule with the kernel trick. After some deduction, we can get the following rule for U's calculation and O's calculation. Pay attention that the function phi and the state s has disappeared, so we can calculate U and O only by the kernel function kappa. So how we calculate U and O in GPUs? The calculation of O is simple that we can use something like flash attention. So the core is the calculation of U. We can use the recurrent form, and we can also use the parallel form or find a trade-off between them. We rewrite the recurrent form of U in a trunk. Then we can find that U of the current trunk is equals to V of the current trunk sub self-tension of current trunk sub cross-tension between current trunk and the previous trunk. Then we can get the last line, which is the trunk-wise implementation. And we compare the three implementations as follows. The recurrent form requires OT loop, which cannot fully use the GPUs. The parallel form requires to obtain a huge metric with size n times n, which needs too much I/O. The trunk-wise implementation needs fewer loops and not increase much flows. And we realize a Triton implementation. We can see that the trunk-wise implementation is much faster than the others. Then we investigated the theoretic abilities of DeltaFormer for state tracking in nonlinear kernel. We can find that using certain nonlinear kernel function, DeltaFormer can track n elements with O log n dimension. While in the lemma 2 of RWKV7, they track 5 elements, use 5 head dimension. And based on our proof, we can find a natural compression for the state tracking. If we can read out and rewrite KU cache every ON step, the actually KU cache is ON log n. Then we do some toy model for the transformer. Firstly is the tracking, state tracking. We can find that even with 8 layers transformer, the accuracy is below 50%, where 1 layer transformer can reach 100%. And any common kernel function is better than transformer. Then we do some interesting experiments that we track n elements with a small dimension. We can find that as the element n increase, the linear kernel has dropped much, and the DeltaFormer with no linear kernel can also do good. Then we find that GQA-like method enhance low linear kernel with the same KO cache. We do the following experiments. We track 5 elements with a KV head with dimension 3, but we have more query, W. As the query number increases, the EXP kernel will gradually do S5 perfectly. Then we do some curricular learning respect to the contextual length. We can find that LP may be beneficial for optimization. That may play a role similar to curricular learning. Then we do experiments about reachability of DAG. We can find that transformer is difficult to learn, while transformer can reach 100% by using the metric inverse. Then we do some experiments about the learning of dark grammar by next token prediction. We can find that transformer has better compression ratio because we think transformer can easily recall whether there are more left processes than the right processes at present. This may explain a phenomenon where a train 500 tokens on a model with a total of 14 billion parameters. We find that DeltaFormer lead baselines by 0.005 in total loss, while lead baseline by 0.03 in code loss. Then we considered the induction heads. We can find that the reformer can learn induction heads more rapidly than baseline. We think that the calculation of U can to some extent replace the function of copy heads, thereby promoting the formation of induction heads. Okay, here are some future work related to DeltaFormer that we have listed. Firstly is the optimization. The metric inverse in DeltaFormer may require more stability training, and we are trying to scaling it. Secondly is some fungi design. Something like group query attention. We have presentation. We have presentation. Maybe we can also try different kernel and compare them. The third is the implementation. Here we try some Triton implementation. Maybe later we will try some CUDA implementation, which might be some faster. Yeah. In summary, we believe that in the short term, we may seek some trade-off in memory capacity and expressiveness. But in the long term, we believe that the most powerful model is likely to be one with strong expressiveness, larger QU cache or state, and more computation. Thank you for listening. Yeah. Okay. If anyone has some question.
Yeah, I think I can maybe ask one question. Maybe the first thing I'm very curious about, many recent papers, they show that the delta rule that go beyond the NC0 and come to TC1. But how we can reflect this ability into some improvement in real world tasks? Yeah.
Real world task, such as Python code evaluating. We know write Python code is a very important abilities of LLM. But the Python code evaluating is a NC1 task. So we think by using data rule or some model with NC1 power, the model can learn Python correctly in pre-training stage. Yes. A few months ago, I think there is a Anthropic's block. They find that LLM do some Python code by uh by some pattern match. I think this may not be intelligence.
I
Yes.
see.
Yes, maybe with data rule, the model can truly learn Python code rather than some memory.
Yeah. I think that it may be more helpful for the pre-training, yeah. Because what one of my concern is on the currently evaluation task, maybe we can see that if we have some state tracking tasks in 81, this seems all can be solved by some maybe RAG or some transformer with chain of thought. Yeah, but if it comes to pre-training that, I think that it's reasonable that you can not even understand data without such data rule, yeah. And
Yes, it's good.
and do you
Good.
think this NC1 is just enough or we need it? Because that from your paper that we have NC2, NC3, that even NCK before we reach to the P, yeah. But also some
Uh,
people ask maybe they be the same one. Yeah, but from the figure that it seems that from the expressiveness we still have a long journey. Do you think that where should we go? Yeah, for real world tasks.
firstly, the common the task the task in the real world it is commonly within NC2. So we may not seek NC3 models, which may can only reach NC2 model is enough, maybe. Then it may be NC1 equals to NC2, just like P may equals to NP. So I think the current stage we may seek models with NC2 expressions, which is enough, and we don't need to seek a model for P complexity because it it's difficult to be parallel in GPUs.
Yeah,
Yes.
makes sense. Yeah. Thank you very much. Yeah, I think there are questions on the chat. Yeah. First,
Yeah.
Zhishan asked, can you elaborate on the language or code experience? What is the baseline here? And he also asked, do you train on standard language data and then evaluate on code data?
Could you
Yeah.
go back a few slides to the loose curve comparison? That slide.
Yes. Due to some reasons, we didn't present it in slides or papers. Yes.
I think
We actually
you have a loose curve comparison in the previous slides, right?
okay. Yeah.
Yeah, I remember there is a slide. So you have
Uh. Yeah. Yes.
so for this loss curve comparison, are you training the DeltaFormer on code corpus or in regular language corpus and evaluated in on the code corpus?
We train on the common language data and evaluate it loss in code data.
I see. So you are still training on regular language modeling corpus and then evaluate in the code benchmark.
Do you
Yes.
have code data as a training? I think
Yes.
there should exist in some mixture, should be starting from the code data. Yeah, if it's a general language model.
Yeah. Yeah, I'm also very curious about like the actual coding performance. Yeah, here you only showcase the complexity of this code modeling. Like I was wondering, are you still working on the evaluation pipeline or did you get some good results on some real world coding benchmark?
For the generation task, we are also in working on debugging on the evaluating systems. Yes. They are because the total actively parameters is small，就是this this this is this 40 billion billions parameters models with only 700 million active parameters. So the actually code benchmark has not significantly. Yes.
I see. So you're using a MOE model and the activated parameters are quite slow to have good performance on real world benchmark, right? Yeah, it makes sense. Yeah, I think like for those coding benchmark, you need a larger model to do well.
Sorry, I think I missed exactly what kernel functions you guys use for your formulation.
Where is our speaker? Oh, I see.
Sorry, I have just lost.
No problem, no problem. Yeah.
Yeah, network issue.
Yeah. Do you see the last questions? He just asked, yeah. And that was a kernel use. It seems that it has been answered in the chat. Yeah.
Yeah, so you're using the exponential kernel for this larger scale training, right?
Yeah, yes.
I see.
Did you guys try other kernels as well?
I'm trying. In toy model, we try them, and they have different performance. But regarding the large scale models, we need to write some treatment implication for each kernel each. It's a very it's a very difficult. So in large scale language model, we only use the softmax extension. Softmax, yes. And we can say that the kernel the the B feature B, we use this kernel. This kernel is from our theory one. It has a very perfect performance, and the feature C is actually the DeltaNet kernel. It has also has a perfect performance in state tracking. And feature D, we try something like ReLU. And with two layers, it has a very perfect performance. And with one layer, it learns slow. And the feature E, we try some XRP, and F, we try some softmax. They they don't have good performance as something like BCD, but they had also good than transformers. Yes.
Gotcha. Thank you.
Do you have
Mm.
any intuition why like a softmax exponential kernel is more expressive than linear kernel, but it learns like much more slower and for many cases cannot learn the optimal solution. Like if you compare figure C and figure F, you can see that like for linear kernel you can easily reach perfect performance, but in figure F, when you use a stronger exponential kernel, and the learning curve appears to be worse.
Yes, you're right, because this experiment we do with when when dimension when head dimension D is larger than the elements. Here, the but if we consider that the dimension D is much smaller than n, the linear linear kernel may have much better performance. Yes, you're
Uh,
right. 对, you're right.
uh,
嗯
so do you think we only need to use like this later nonlinear kernel function instead of the exponential kernel? Maybe we can just use this linear kernel with a rounding function.
Yeah, yes, I think is I think we can try this, but
I think it would be very interesting to have a language modeling experiment also with this I call it rounding linear kernel, right?
yes, but rounding linear kernel is very difficult to optimization. We try this in small language models, and it has some issues. Yeah.
Okay, so you have some vanilla implementation, and you actually tried it on language modeling, but it doesn't the loss doesn't get down, right?
Yes.
I see. So it only performs well in those toy-rich benchmark, and then you find okay, for language modeling, it's still need exponential kernel. I think this may be related to the memory capacity, right? Because like softmax exponential kernel has much larger memory capacity, and for language model, this sort of memory capacity is kind of important.
Yeah. Yes, I think so. Yes.
I guess I have another question. So far, I know a lot of us have all explored different maybe expressiveness architectures. And I haven't really thought about this before, but your talk made me think, do you see a future where maybe we have a unified architecture that can selectively decide between expressiveness and kind of parallelism on a task or token basis? Like we don't have anything like that. Everyone keeps, looking at like a kind of a single modality. It's a sort of a new kind of multimodal where we would have like a different expressiveness modality that might be employed depending on the inputs. Do you have any ideas on that, or like what kind of direction might lead to those kind of models?
Uh, it's a good question. Yes, some task is very simple, which may use some simple model, and some task may be very complex that we may need some powerful model. But regardless the detailed implementation, I don't have much clear ideas. Yes.
Yeah, the interesting thing in my mind about that is how we could train a model like that. Your paper in some ways talks about there being like a variety, almost like I don't know, like a range of expressiveness choices as we change the formulas, and we can trade off parallelism for expressivity. And I wonder if there's a way that we can think about how to train a model once that would give it the option to, smoothly change between these kinds of expressiveness forms without having to have like, 20 different models for each different kind of formula. So I don't really have any great ideas on that, but it just occurred to me, so I thought I'd bring it up.
Yeah.
Maybe I think the next block diffusion model will be some kind of the alternative. Yes, if you can choose the block size dynamically, so the model can change from the P complete or the TCK in my mind.
And I think if for the current model that because that if you add or just remove the delta rule that is still exp kernel with the softmax attention. So I guess that if you, for example, if you know that this task is difficult or easy and you choose to add or insert or do not insert delta rule, maybe it can also be adaptive between two computation. I'm not sure about it, but from the formula, it do not have a very huge gap. Yeah.
That's a really good point. And maybe, usually when we see these things trained for other kinds of uses, it helps to, during training, expose it to a range of different kinds. So maybe if during training, you range from like fully softmax to some hybrid and show it both of them, then maybe it can use both during inference and selectively decide somehow.
I think there's a ICML paper discussing related issue like how to dynamically decide when to use attention and when to use linear attention.
Oh, cool. That sounds great.
Yeah, I'll send it in the Discord channel later. And I think there's an incoming paper also dynamically deciding. Oh no, it's not a dynamic deciding.
Statically, yeah. Noted.
Yeah, I think it's always interesting to like for different tasks, the model can dynamically decide whether to use efficient model or supervised attention or even expressive variant like DeltaFormer. Say if the model sees some input with very difficult math problem or coding problem, the model can switch to DeltaFormer. And when the model sees some daily life like chat, and the model can even simply just use linear attention to solve this problem. Yeah, it's very interesting to switch between different models based on the difficulty of the input sequence.
Yeah, and I think the other interesting view of all of this is like getting back to everyone's experiments on sparsity also, and both of these things, and versus like kind of the compressive memory view of things. And in a way, these are all sort of, in my mind, kind of dual to each other, and there's some kind of sliding scale about what you compress versus what you keep. And I guess when we're talking about doing it dynamically at inference, then there's some question of, do you keep a single compressed memory that you can use optionally, and what is ideal there? Or do we keep kind of like multiple stages of compressed memory somehow? And what's the optimization trade-off? So I don't, it's something interesting to explore. I'm curious about it.
Yeah, I think this is definitely worth exploration in the future.
Yeah, and I think there are multiple dimensions. For example, if you switch from softmax attention to DeltaFormer, you just want to improve the expressiveness, but not maybe some more advanced memory. But if you shift between attention and maybe the linear attention, that maybe you are maybe wants to some more memory ability and some maybe other bit, so that maybe there are so many disentangled directions on the design space, yeah, with different capabilities.
Yeah, and that's not even including the idea of expanding the memory size, in like using like any of the kind of like based or other kinds of approximations to exponentiation, so that we can kind of achieve the same idea but through a larger memory. So I don't know, it's interesting because to me it feels like all of this is very malleable and like a smooth gradation like across, it's like there's like a spectrum of how much memory you have, and transformer is on one side of it, but it's missing some expressiveness. Whereas if you can operate on the memory, then you get that expressiveness. And I guess there's at least like, yeah, a couple of dimensions there that could all be changed, possibly at real time, or so far a lot of us I think are looking at it in a pre-training kind of manner. But it's interesting to think about how we could smoothly change it during runtime.
Yeah, this makes sense, yeah. Yeah, I think I have one more question that is about also maybe related to evaluation, because that I think currently that when people show the advantage of this maybe expressiveness models, that they just exclude the maybe chain of thought, but chain of thought is a very common tricks of the LM these days, although we know that it can reach the P. Do you think that if you include chain of thought, what will be a good way to evaluate the performance gain of maybe the data former? Maybe some shorter chain of thought, or some tasks you do not need a chain of thought, something like this. I'm not sure.
There, as an evaluation, there is a benchmark I think I remember in this year in February about multimodal. It's about state tracking. Then the GPT-so will reach random without chain of thought, but with chain of thought, they can reach nearly 100%. I think in the future we can also try some use some benchmark within a target computation. Then we may find that for DeltaNet related some models, it can solve some NC10 with much slower decoding step. And a few days ago, I remember that Yuan Dongtian published a paper. He considered the continual chain of thought in DAG reachabilities.
Yeah, that's right.
Yeah, yeah. He thinks that the vanilla transformer needs O(n) square step to decide the reachabilities in a DAG, and he thinks that with a continual cell chain of thought, it only needs OD step. Where here we may think D is equals to N. But if we have some NC1 task, it can it can have it can have decided the reachabilities of a DAG in one step without any chain of thought. So we can think that the efficiency is very high
Yeah,
for
I know this. Yeah, I think
NC1.
this is an important point that currently that we should incorporate chain sort and show the efficiency performance trade-off. Yeah, which should be better. Yeah.
Yes. On the other hand, I think the chain of thought or O1, we need many data. There are many data we need a human to create. Maybe for DeltaFormer or some alternate, the best the best training data for the model is different from the data we see today. I
Yeah.
think. I think because the base model may be much smarter, the we don't need to create data step by step. We may skip some step.
Yeah, this is reasonable.
Yeah, I'm not sure. Hmm.
Yeah, I think this is also related to maybe another problem when people do distillation that one recent paper that when they distillation on masters, they find that if you use the QWQ search duplicate for this distillation, it's even better than maybe the DeepSeek R1 or even Gemini that but maybe this is also the problem that the larger model or more expressiveness models that they can skip some internal steps. So some maybe calculation or some steps may be easy to them. But when it comes to some weaker model that it is something they cannot be learned. Yeah.
Yes.
Well, I have a question. Do you try this dot former on other downstream tasks like time series forecasting tasks? Or,
No, we haven't yet. We only try some toy model and language model pre-training. Maybe in the future we will try this. This is a good point.
uh, or, did you try to compare this architecture with other models like a Mamba? Or
Model and member. If you say the low no linear model, linear model, I think it's difficult to parallel in GPUs. So I think it's difficult to become the core component of modern language models. Uh, Considering Mamba, I think is interesting, but I think there is paper that which proves that Mamba is within TC0. So it is difficult for Mamba to perform some task like state tracking or something else in which is one conflict. Yes. Yes, if we have computing resources, we will compare the Mamba. Yeah.
Also, another question is that for transformer or for current language models, they they don't work well on math problem or understanding the numbers. Do you see maybe DeltaFormer might have potential to have maybe better performance on those tasks, like math problem or?
Yes. I think so. For example, calculation is a task is a task or count is a task in TC0. Then transformer with low precision is within AC0. So we can find that transformer is difficult to count. Hey, if we had some, I think if we use something like transformer, they may have better abilities in count and may be beneficial for other math abilities. I'm not sure. On the other hand, because DeltaFormer or sounds or DeltaNet, it can have the abilities to decide the reachabilities in a DAG. Then, if we list some step in the contextual, may DeltaFormer or DeltaNet can will know if we can solve these problems directly. I think this machine may help model to think faster in math problem. Yeah. Yes.
Okay, cool. Thank you.
Mm.
If there is no more questions, I think that we can end today. Yeah, I think that data former is just maybe extension of existing transformers that may become more strong, and we can hope that whether it can be used in most cases in the future. Thank you for all the audience and the speaker today.
Yes.